number 24, graphing number 24. Let me start with this though. The starting point is you're supposed to remember what the graph of y equal to ln x look like. Okay, it looks like this. That's the inverse of e to the x, right? It looks like this, approximately.
There's no image.
Hold on.
Yeah, we're still on the.
Oh, thank you. Yeah, it looks like this. Thank you, thank you. So it looks like this. Okay, that's a y equals to ln x. Now, 23b is more about 23b is your understanding about transformation. What is the graph of negative ln x? Well, basically, this is the basic function. If you put negative in front of this, multiply the whole function by -1, what happened to the resulting graph? And basically, it becomes upside down, right? It becomes upside, oops, no, not this one. You flip with respect to x-axis. So negative ln x will be upside down. So your pre-calculus teacher is supposed to be strong. Okay, supposed to be strong, right? Reflect y equals to ln x graph with respect to x-axis. Okay, when we reflect with respect to x-axis, the x component stays the same. The y component becomes -y. So the original function y equals to ln x, when you reflect with respect to x-axis, the y becomes -y. Okay, which is equivalent, this statement is equivalent to y equals to negative ln x. You see what I mean? Okay, now using that same idea, how about number 24a? Y equals to L natural log of -x. So notice that this is basically y equals to ln x. Then you change the x becomes -x, right? But the operation of replacing x by -x is actually reflection with respect to y-axis. Okay, when you reflect with respect to y-axis, like let's say you have coordinate here, call this, let's say, this is 3, 2, let's say. When you reflect with respect to the y-axis, the x will becomes negative, but the y stays the same. Right? Okay, so in general, when you reflect with respect to y-axis, then the x will become -x, while the y will stay the same. Okay, which is what happened in this equation from the original y equal to ln x becomes ln -x, right? So then look back into that y equals to ln x. Now reflect this with respect to the y-axis. So it will look like this approximately. Okay. So this will be something looks like this. You reflect that ln x graph with respect to y-axis. Now, how about number 24b, Thomas? Number 24b. where we have y equals to natural log of absolute x. Now we learn from pre-calculus again. So you see, you cannot run away too far from pre-calculus, huh? Absolute of x is equals to x for x greater or equals to 0. When it is positive, that as is. When it is negative, then you apply another negative to make it positive. Right? So basically, this function can be rewritten as y equals to natural log of x when x is positive or 0. That's natural log of negative x for x is negative. But again, the idea is actually coming from here. Okay. Now you think about this as a piecewise defined function. You see this as piecewise defined function. On the positive side, 0 to positive, it will just be the graph of ln x. Just the graph of ln x, approximately like this. Right? And then on the negative branch, it will be just the reflection of that graph with respect to y-axis. So this is y equals to ln x. This is y equals to ln negative x. But together, it will give you, both of these together will give you the graph of y equals to ln absolute of x. So that's for number 24. Okay, that's for number 24. Other question? No more? Okay, then I pick questions then. Let's see. If you have any question, let me know right away. Okay, just interrupt me.
So with the one you just did with absolute value of x, so you would need both those lines for it to be ln absolute value of x.
That's right. Because absolute of x has this on this region and is equals to negative x on this region. Now applying ln natural log, basically applying natural log to both branches. Okay.
Okay. I guess my brain's trying to see the absolute value and disregard the negatives, and it shouldn't do that.
Absolute value of x, when we try to graph that, it looks like this. Okay. I mean, most of us already know what absolute of x looks like, but have you ever think about why the graph looks like this? Absolute of x, y equals to absolute of x looks like that, right? Okay. But the explanation is because on the positive branch, that's a line through the origin with slope 1. But on the negative branch, that's a line through origin with slope -1. Okay, so this branch here give us this line. This branch here give us this line. Okay, okay. Now then when we apply natural law, it will give us this branch on the positive line, the positive side. It will give us this branch on the negative part. But both of them together is the graph of natural log of absolute of x.
Okay, okay, thank you.
If you have no more question, let's do some easy one. The thing is, like, I don't know how easy is worth mentioning here though. Number 4a. Number 4, we have natural log of 1 over e. You have two ways to do this. The first one, you use rule number 2, natural log of 1 minus natural log of e, which is natural log of 1 is 0, natural log of e is 1, so this is -1. That's the first way. So we know the answer is -1. Another way to look at this, the second method, is you say this is natural log of e to the -1. Basically, you rewrite 1 over e, and then you use rule number 3, move the negative to the front. Okay, that's for number 4a. Number 4b, log base 10 of square root of 10. This is equal to, actually they don't need to write this base 10 here. If they don't write base 10, it means it is base 10, even without writing the base. Okay, if they don't write the base and they use log, it means it's base 10. Now, we can see this as log 10, base 10 of 10 to the power of 1/2. Right? By one of the basic property, this is equals to 1/2. If you want to see better, you can move the 1/2 to the front using rule number 3. And log base a of a is equals to 1. Okay, so you have 2 different ways to do this, but I think the first way is better. Okay, now from number 4a, actually, we know the following. Log for whatever base of a over c, maybe I use x over y better, x over y is equal to negative of log base b of y over x. If you think about it, it's because of the following. X over y is the reciprocal of y over x to the power of -1. Right? To the power of -1. So log base b of x over y is equal to log base b of y over x to the power of -1. Right? Which I can move the exponent to the front. Okay, that's the little proof. When you do the reciprocal of logs, then the argument of the log, then you get the opposite sign. What else? How about number 8a? Number 8a. This is e to the power of -2 natural log of 5. We learned this. One of the basic property we have is base to the power of log base b of x is equal to x. Okay, now, so using that, let me massage this expression this way. This is e to the ln 5 times -2. But that expression is the same to e to the ln 5 to the power of -2. Now, inside the parentheses, that's 5. That's 1 over 5. Okay, how about solving equations between number 27 to number 38? Let me ask you to pick questions. Between number 27 to number 38, pick 3 or 4 questions. Somebody pick the question. Okay, let me do number 28A. Solve natural log of x squared minus 1 equals to 3. If you have natural log on one side and constant on the other side, then you change that into exponential form. So x squared minus 1 equals to e cubed. That's the exponential form. X squared equals to 1 plus e cubed. So x equals to plus minus square root of 1 plus e cubed. Okay, now, but before you're done with your answer, make sure you check if the x is in the domain of the natural log, in the domain of the equation. In other words, the argument of the log has to be positive. Okay, but the way we set it up here, it will be positive. So both answer will be okay. Okay, so x1 is square root of 1 plus e cubed, while x2 is negative square root of 1 plus e cubed. Now, I didn't say that the solution has to be positive. No, the solution may be negative as long as the argument of log is positive. Okay, keep that in mind. That's for number 28A. Let me see, how about 28B? 28B, e to the 2x minus 3 to the 3 times e to the x plus 2 equals to 0. The thing is, notice that this is actually e to the x being squared. Do you notice that? Okay, so you can use substitution if you like. You don't have to, okay, but you can say let u equals to e to the x. If someone is ugly, substitute with u. Then if you do that kind of substitution, you will get u squared minus 3u plus 2 equals to 0. And then you factor it. I don't forgive you in this if you don't know how to factor this simple case in my class. Okay, no forgiveness. You need to know this. So u equals to 2 or u equals to 1. Now I substitute that u back to e to the x. So e to the x equals to 2 or e to the x equals to 1. Well, e to the x equals to 1 means x equals to 0, right? E to the 0 is 1. But this one here, x will be natural log of 2. Okay, so it's actually a quadratic-like equation type, but they sneak in exponential function. That's for number 28. Can you suggest me other question to work on?
Can you do number 30?
I can do number 30. Number 30. Number 30A. Number 30A, solve for x. E to the 3x plus 1 equals to k. Now, assuming k is positive, okay, because e to any power, the range of e to any power is positive, right? So assuming k is positive, strictly positive. If k is 0 or negative, then there's no solution. Okay? Yeah. But if k is positive, I need to get the exponent. How to get the exponent? Apply natural log. You change this into log form. So natural log of k equals to 3x plus 1. And then you subtract by 1, divided by 3. Natural log of k, subtract by 1, divide by 3 is dx. My equal sign, I need to make it straight. So natural log of k minus 1 over 3 equals 2x. This is actually not the only way to do it though. That's not the only way. The second way to do it, but this is more hassle. Actually, you happen to see, oh, 3 to the 3x plus 1 is 3 to the x times e to the 1. E to the 3x times e to the 1 equals to k. So you divide by e first. And then you apply, convert this into log form. So natural log of k over e equals to 3x. And then you divide by 3. But natural log of k over e is natural log of k minus natural log of e, which is 1, right? Okay, so natural log of k minus 1 over 3 equals to x. Just more work. But we still come up with the same answer. That's for number 30A. How about 30B? Log base 2 of mx equals to c. Now I need to solve for x. Change this into exponential form. So be flexible with this when you solve exponential and logarithmic equation. Okay, sometimes the trick is simply change it into log form, or from log form change it to exponential form. So x equals to 2 to the c over m. Or your textbook may write it as 1 over m times 2 to the c. Okay, but it is just that simple. Okay, that's for number 30. Any else?
Thomas,
Uh-huh.
in order to get the 2, I guess a solid 2 on the right side, what did you do?
The one here?
Yeah.
Oh, I changed it into exponential form. Yeah, okay, let's see. Exponential form b to the x equals to y, that's exponential form, has logarithmic form log base b of y equals to x. So you see the base is here.
Mm-hmm.
Okay, the exponent is here. And then the answer is, the argument is here. So if you kind of like see, this is the base. I color it. Okay, this is the base. This is the argument. This is the argument, and this is the exponent.
Oh, okay.
Right. So
I
I
see.
play with that kind of game.
Okay.
Yeah, I play with that kind of game. That's what I did also in 3A though. Number 30A. That's what I did. Okay. So don't forget this one. Important. The idea is way too simple. To be honest with you, when I first learned logarithm, I didn't really think that way. When I try to solve, let's say, to solve this one, right? Log base 2 of mx equals to c, I tend to do it this way. Oh, you know what? Make it exponent. So 2 log base 2 of mx equals to 2 to the c. Okay, some people did it this way even until now. Yeah, even until now. Okay, I did it this way also before, and then I say, oh, one of the properties say that base to the log of the same base cancels, give us the argument only. Okay, that's how I thought before. But if you think about it, let's basically change from logarithmic form into exponential form. That's all we did.
Oh, okay, I see.
Right?
Oh, so it's almost like if It's because it's been a while since. I mean, I remember this. It's just been such a long time since I saw this. But
Yeah, it's pre-calculus.
yes, I know. That's why I remember
Yeah,
it. It's just
at least half a year ago. Yeah,
yeah,
so
literally, and
that's why this book actually reviewed that.
oh,
Okay,
okay. Yeah, it's
that's
like
why this book reviewed.
it was during the pandemic.
Always blame it on that one if something goes wrong.
It's easier to blame it on that.
Yep. I am with you. Okay, so you don't blame me, okay?
No, I don't blame you. I don't blame you.
Okay, other question maybe?
I'm wondering about the inequalities. I haven't done it with inequalities. 39.
Okay, yeah. So let me just move ahead with the inequality. But before I do that inequality, let's make this following observation first. Important observation. Observation. Okay, now I will start with increasing function, maybe decreasing function. Y equals to 1 over x is decreasing, right? On the positive branch, it looks like this. On the negative branch, it looks like this. It is decreasing. On the other hand, y equals to, let's say, square root of x is increasing. It seems like what I'm doing here has nothing to do with what we're going to do in this inequality, but it's actually very closely related. Okay, it is increasing. Now, what I want to show you is the following though. If the function or the operation is increasing, then the inequality will be maintained if you use that operation. For example, we know that 2 is less than 5, right? Consequently, because we have square root, which is an increasing function, then square root of 2 for sure is less than square root of 5. Because square root is an increasing function. Okay, now 1 over x is decreasing, so that when 2, we know 2 is less than 5, right? But the reciprocal, 1 over 2, will flip the inequality sign. Does it make sense? Okay, it has to be greater than 0 too.
Yeah, that does make sense.
Okay, now using that idea, apply that to exponential and logarithmic. Okay, d to the x is increasing for base greater than 1. It is decreasing when the base is between 0 to 1. Likewise, logarithmic function log base b of x is increasing when the base is greater than 1. It is decreasing when the base is between 0 to 1. Now, how do we use this property then? Okay, let's see, for example, number 39a. Natural log of x is less than 0. Okay, but natural log, the base is e, which is greater than 1. Okay, so when you apply exponential, e to ln x is less than e to the 0. The guy on the left-hand side is x, the guy on the right-hand side is 1. Now notice that you need to be careful here. Okay, this is true because e is greater than 1. That's why we maintain the inequality. Okay, suppose I change the question. Instead, log base 1/4 of x is less than 5, for example. Okay, but log base 1/4 is decreasing, right? 1/4 is between 0 and 1. So that log function is decreasing. When I apply the base 1/4, right? So x, I need to flip the inequality. 1/4 to the 5th. Okay, so x is greater than 1/1024. Okay, I hope you see why this question is actually not that simple. The question in our book is actually just simple because the base is always greater than 1. Number 39A, 39B, number 40A, and 40B. Right? Let's see number 40A. So 1 is less than e to the 3x minus 1 is less than 2. I apply natural log to all sides. Natural log of 1 is less than natural log of e to the 3x minus 1 is less than natural log of 2. This is 0, less than 3x minus 1, less than natural log of 2. Do you see the process? Right? But I maintain the inequality sign. I don't need to reverse it because base e is greater than 1. Therefore, the log base e is increasing. Okay, I don't need to flip the inequality sign. And then we divide by 3. I cannot teach this increasing, decreasing idea to anything less than pre-calculus because students in algebra level, they don't have that foundation. Now, you already have this foundation, so I hope you understand why this is true. Okay, because it is increasing, because it is decreasing, the further you go to the right, the smaller your y value, right? The further you go to the right, the smaller your y value. Okay, so I have to say that this question is something I actually reserve for after I'm done with that inequality, with the equation. How about part B? Similar 40B. 1 minus 2 natural log of x less than 3. So 1 minus 3 is less than 2 ln x. I basically move this to the right and I move this to the left. That's what I did. Okay. Then on the left hand side is negative 2 divided by 2 becomes negative 1. So negative 1 is less than ln x. Okay, so e to the negative 1 is less than x. Or another way to say it, x is greater than 1 over e. Now, some of you may have done it slightly differently. You subtract by 1 instead. That's fine. Negative 2 natural log of x less than 2, right? But then you divide by negative 2, right? When you divide by negative 2, don't forget we flip the inequality sign, right? Okay, so x is greater than e to the negative 1, which is 1 over e. That answers a big question we have long time ago in Algebra 1. Why, if we multiply or divide an inequality by negative number, why do we need to reverse the inequality sign? In Algebra 1, when students ask me this, I actually have this question myself when I learned inequality. And I remember my teacher actually gave me this example. Thomas, instead of answering you in abstract notion, let's do non-abstract one. 2 is less than 5. If you multiply by -1, and 2 becomes -2, 5 becomes -5, which is greater. -2 is greater. You see that inequality flip. Okay, now, now get off. I don't want to see you anymore. That's what he said. That's what he said. I remember that my teacher just sent me out from his office. Okay, this is the example. That's it. Get out of here. But of course, this is, while maybe you happen to choose 2 and 5 and happen to work like that, and when you choose other numbers, it doesn't work that way. Okay, so let's see the idea. When you multiply a number by -1, you basically do this operation. Right? The new number y is the opposite of x, but y equals to -x, we know is a decreasing function. It's a linear function with slope -1, right? Does it explain? Okay, so when you multiply by negative number, okay, when you multiply by negative number and operation -x is decreasing, that's why you need to reverse the inequality sign. Okay, that's a better theoretical and abstract explanation. Now, I don't think you can find this kind of explanation anywhere. But that's actually the explanation. Okay, I hope this way we solve the inequality issue. It's actually not too hard though. It's actually not too hard. Oh, you just need to be aware. Oh, you know what? If we do this transformation, it's a decreasing function. So reverse inequality sign. If I do this transformation, it's increasing. So I don't need to reverse it like that. Okay, that's for number 40. Any else from here? Let's do the limit thingy then. Between number 47 to number 52. Between number 47 to number 52. Well, that's actually an interesting question. Number 48. Number 48. Limit x going to 2 from the left-hand side of log base 5 of 8x minus x to the 4th. How to do this problem? I believe there's more than one way, but let's see a better explanation. I think I can factor the x out from the log, right? So this is equals to limit x approaching 2 from the left-hand side of log base 5 of x times 8 minus x cubed. Is it okay? And then this becomes limit x going to 2 from left-hand side of log base 5 of x plus limit x going to 2 from the left-hand side of of natural log of 8 minus x cubed. I see this as product, log of product, right? Log of product. Now this one here is just log base 5 of 2, right? The one on the right-hand side is, how did log becomes natural log? I don't know. Maybe because of evolution. I believe in evolution because of this kind of, not because of the theoretical explanation from those biologists, no. It's because I just change it like this. And then if in 5 minutes it can change into natural log, then what happens if you give me 1 million years? I make up stories. Okay, now the problem is this here. So what happened if x is approaching 2 from the left-hand side? What happened to x cubed? X cubed will approach 8 also from left-hand side. Right? Okay, slightly less than 8. Slightly less than 8. So 8 minus x cubed, okay, will be 8 minus something slightly less than 8. That will be 0 from the positive side. Is it okay?
Is it zero? Is it zero on the positive side because of the two negatives there?
Not because of 2 negative, no. Because you will have 8 minus something slightly less than 8. Because this is 8 that is closer from, like approaching from the negative side. Right? Okay, so let's say 7.9, you know, or 7.99999. Okay, so 8 minus 7.9999, it's very close to 0, but positive. Right? Okay, now then, so this is basically limit y going to 0 positive of log base 5 of y.
Thomas, if I may, this is one of the ones that I had a question on when I was watching the lecture on the video. Because I was still a little confused as to why we had to convert it on that. Why did we change it from limit as x approaches 2 from the left side to y as it approaches 0?
You don't have to. You don't have to. You can just leave it like that. You can just leave it like that. But how do you express this when x going to 2 from the left-hand side? I mean, will you allow me to say that this is actually log base 5 of 0 positive? Will you allow me to write it that way? Because that's basically what happened.
Would that come from inputting the 2 into the x, and then you would get x 8 minus 8 equals 0?
But the thing is, like when you input, the thing is log base 5 of 0 is undefined. It's undefined. Okay, so plugging x equals to 2, while actually x approaching 2, not 2, will give you undefined answer, and that's not what you're supposed to do.
How would I be able to recognize in that case? I probably wouldn't have recognized that log 5 log base 5 0 would be undefined.
Well, because you need to memorize the graph of log function.
Okay.
Yeah, log function, the domain of log function is positive number. Cannot even be 0. Not including 0.
Okay.
Right? Okay, so yes, it goes back to your algebra 2 and your pre-calculus actually. But
So
no, I'm not saying that you should not. If you forget it, then something wrong with it. No. It's been a while. You do exponential.
Yeah. So
right?
that's why I just want to make sure that I allow myself the I guess the tools. So if that's one of them, that just to make sure that I'm familiar with the log function graph.
Yeah. So the log function, the argument of log has to be strictly positive. Cannot even be 0. So when it says that x approaching 2 from the left-hand side, of course, visually, we try to plug that in first. What happened when x equals to 2? Or I get the argument becomes 0. Oh, no, I cannot do it that way. I have to go slower. You see? Right?
Okay.
Then I said, oh, you know what? Then instead of just plugging x equals to 2, let me take a look what happened in the limit condition. Okay, so when x approaching 2 from the left-hand side, it means 8 minus x cubed approaching 0 from the right-hand side. Okay, so I will get limit 8 minus x cubed approaching 0 from the right hand side of that log base 5, 8 minus x cubed. Now, then once this guy is the same to this guy, let me use different color. Once this guy the same to this guy, then you can use dummy variable or simply replace that. Okay, so you replace this expression by 0 positive, but log base 5 of 0 positive is what? Log base 5 looks like this, right? Now, when x is approaching 0 from the right-hand side, what happened to the y value?
Goes to infinity.
Negative infinity, that's right. Okay, that becomes negative infinity. Okay, it's supposed to be negative infinity plus log base 5 of 2, but negative infinity plus any constant will still be negative infinity. Okay, maybe the negative infinity is not as negative anymore, so a bit smaller. Okay. So for example, infinity plus 5, it should be greater, right? So your infinity sign should be a bit bigger, okay? You know I'm joking. Infinity, however big you write it or however small you write it, it's still infinity.
So what was so log 5 of 2? It's
just a constant. It's just a constant, right? Maybe positive, maybe negative.
Oh, it's just like how you mentioned with infinity plus 5 equals infinity.
That's right.
Okay.
Yeah.
So you mean to tell me that on the schoolyard growing up, every time we said infinity plus 1, it didn't count?
However hard you work, if you already infinity, doesn't matter what you add. Hey, that reminds me to a news that I read on Facebook. That's kind of a strange way to get a news. But there's a class in Afghanistan where people die, like 30 students die. 30 students learning to make a bomb. To make a bomb. Died because the bomb exploded. Exploded. The question is, what grade they're supposed to get? Should they get an A or F? It's like this is I mean, I read it on news on Facebook, and of course my interest is with the comment, right? Sometimes the comment is just so funny. I mean, it's not that it's how to say it. It's like, it's not that I don't feel bad when people die, but it's like, as an instructor, because it's my professor, it's my dissertation professor at USC is the one sending it to me. Not only to me, of course, he posted on his page, right? And he make that question. It's like, so what the student should get, right? They bought the test. Right? But they are taking class where the bomb's supposed to explode. Okay? But they bombed the test. So are they supposed to get an A or supposed to get an F?
I think it's undefined.
Well, my answer is incomplete. They didn't submit the test.
Technically, they succeeded, but they didn't succeed.
Yeah, okay, you tell me. So the limit is.
But do they get points for the effort, or are you gonna end up deducting on this one?
It's an A because they were successful in creating a bomb that they themselves cannot survive.
I'm pretty sure safety is part of every class.
Well, you can say it that way too, right? Safety is part of every class. So if that's the case, then they're supposed to get an F. But the purpose of that class was actually to create a bomb that kills. They forget to say that you still need to be alive. So the argument for that, so I know it starts with like a joking question, but it makes us focus on what is the purpose of the class. What does the syllabus of the class say? Okay, is the purpose is to create a bomb that explodes, or the bomb that explodes and you are still alive? Okay, now apparently that well, they just need to create a bomb that explodes, so they're supposed to get an A. Okay, even before the final. Well, anyway, this is not a good story, but I'm just telling you, when I assign a grade, for example, right? Okay, it's really based on how you argue your case, how you show the work. Okay, it's not about do I like you or not as a person. It doesn't matter. Okay, so some people like I don't want to make Thomas piss off. It's one thing that if you piss me off as a person, but as a student, I still have to grade you the way I grade other people. Okay, so no, you don't need to have the same opinion with me, even in this story. Okay, even in this story. For the math part, of course, you have to agree with me, but other than this, don't worry about it. Okay, what else? How about number 52? I think I have too much story such that I kind of like too slow in this section. Limit of x approaching infinity.
No, I think it's a good thing. It gives us a break for our brains to come back together and rebuild.
Okay, but using a bomb as an illustration, I don't think so though. Number 52, we have this. Now, don't plug in infinity because you will get natural log of infinity minus natural log of infinity. It can be anything. It can be anything. No, that's not the right way to do it. Okay, the better way is limit of x going to infinity. The guy inside the bracket can be condensed into a single log. Is it right? And then at infinity, natural log of this function, basically this function is continuous, so I can pull the natural log out and apply the limit into the argument. Now, be careful when you argue here. When you show your work, do not just say, oh, you know what, limit of this is equal to 1, and therefore this is natural log of 1, therefore this is 0. No, I will cross this one out. Why? If you do a step where you have limit and all of a sudden in the next step you don't have limit, the interpretation is you apply the number into the function. So basically you are saying that 2 plus infinity over 1 plus infinity is equals to 1, but that is not true. That is not true. That's not the argument. You need to be a bit slower. Okay, that's not how you show the work. You're supposed to do it this way. Okay, well, if I plug in infinity, I will get infinity over infinity. Not a good idea. Let me go slower. So I divide the top and the bottom of that rational expression by x. You see this? Now then, when you apply infinity, what will happen? There will be 0 plus 1 over 0 plus 1. That's how it's supposed to work. Okay, and this is natural log of 1, which is 0. So the main purpose, the main topic for this question, actually, what do you do when you have this limit situation? This is actually a calculus 1 question, not calculus 2. How do you show work for this? You cannot just say, oh, this is equals to 1. No, that's not the right way to show the work, even though the answer is 1. But the proper explanation is you make it over x first. Divide the top and the bottom by x, such that when you replace x by infinity, once the limit disappears, it means you replace the variable x by infinity. Now, when you replace x by infinity, this becomes 0, this becomes 1, this stays 1, this is 0, this is 1. Okay? Now, what's wrong with this argument, Thomas, if I show it this way? If you show it this way, you see that the limit suddenly disappear. It means you are saying if the limit suddenly disappear means you replace the variable by the infinity right away. But this is not equals to 1. That's not equals to 1. Okay, you can try this. Instead, I change the expression. Okay, if I change the expression, limit x goes to infinity of 2 plus x squared over 1 plus x. I dare you substituting the x by infinity. Is it equals to 1? No, it's not. Okay, because infinity squared should be a lot bigger infinity, right?
Why is infinity? Why is 2 over infinity equal to 0, or 1 over infinity equal to 0?
2 over very big number. The graph of 2 over x. The graph of 2 over x looks like that. When x very, very far to infinity, then the y very, very close to 0. Limit x going to infinity of 2 over x is 0.
Yeah, I was gonna ask about that. So it's basically just because we're dealing with the limit in this case. That's why.
Yep.
Graph. Okay. And
Okay.
then I was gonna ask also, like on that example that you were giving us of the 2 plus x squared over 1 plus x, and we're always dividing by the whatever the x in the denominator is. So like if it would have been x squared on the bottom, would we have used x squared instead, or do we just go based on the lowest?
Actually, divide by the highest exponent. Yeah, so we will divide by x squared instead. So the proper way to do this question is dividing by x squared. Limit x goes to infinity of...
Always the highest exponent, regardless of whether it's on
there are different ways to actually do that. But in this case, if you divide by x, you will get this. If you divide by x. Okay, which I don't really like because you will have 0 plus infinity over 0 plus 1, which is infinity over 1, which is just infinity, which is the answer. However, if you divide by x squared on the top and the bottom, then you will get limit x going to infinity of 2 over x squared plus 1 over x squared plus 1 over x, which will give us 0 plus 1 over 0 plus 0, which is 1 over 0. Okay. Now that will give us infinity with a notion. You know what? Let me write it more properly. Give me a second.
This is gonna sound like a silly question, but why did you multiply the top and bottom by 1 over x?
So that I don't reach infinity.
Because I do remember that part from calculus. It's like the 1 over x would will equal to 0. Oh, see, that makes a lot more.
Yeah.
Okay, yeah.
Okay, so 2 plus x squared over 1 plus x. Now this will be limit x going to infinity of 2 over x squared plus 1 over x plus 1, oh, I'm sorry, 1 over x squared plus 1 over x. Now, but when x goes to infinity, what happened to 1 over x? When x goes to infinity, what happened to 1 over x?
0.
Approaching 0 from the positive or negative side?
Positive. No,
From
wait.
the positive side. That's
yeah.
right.
Oh, okay.
Right? Because x is positive, very big positive number, so 1 over x will be very small, still positive number.
Mm.
Okay, so it will be 0 positive here.
Mhm.
Okay. Now it will look better once we substitute that 1 over x by, let's call that u or y or t, doesn't matter. Let me use t. So limit t goes to 0 positive of 2 t squared plus 1 over t squared plus t. Then this will be 2 times 0 positive plus 1 over 0 positive plus 0 positive. At the bottom you will get 1 over 0 positive, that's infinity, not negative infinity. Okay. 1 over 0, don't get me wrong, 1 over 0 is not positive infinity. No, it's undefined. Okay, 1 over 0 negative, approaching from negative side, is negative infinity. Okay. Be aware with that little detail. That's why I need that positive sign there. Okay, that's why I need that
That
positive sign.
indicates that it's dealing with the limit, which is what makes it up.
Yes, that's right. Okay, let me move on. Number 54. Number 54. If we have fx equals to natural log of x plus natural log of 2 minus x, what's the domain? Remember, the argument of natural log has to be positive. Okay, so x has to be the set of all x where x is strictly greater than 0. And at the same time, 2 minus x has to be greater than 0. Okay, so has to be greater than 0, but if you solve this, then x has to be less than 2. Right, so the domain is basically only from 0 to 2, not including the endpoints in interformation. Okay, so for example, if you plug in x equals to 10, it will be okay here, but 2 minus 10 is negative, then it doesn't work here. Right? Okay, so remember the argument for log is strictly positive. Number 56, I think that's an interesting question.
Quick question, Thomas.
Okay.
So for the domain, I have like a decent understanding of how you got it, but I don't know if I would ever be able to write something like that. Would you have another way of finding the domain from there, or
think of it this way: from precalculus, like the domain of the sum of two functions, or the difference of two functions, or the product of two functions, equals to the intersection of the domain. Intersect the domain of gx. So what I did, basically, I find the domain for this, intersect that with the domain for this.
Oh, I see. Okay.
right? So it has to be greater than 0, but at the same time, it has to be less than 2. Okay, so that's what I actually did here. It's actually coming from this. Now,
Okay.
keep in mind that it doesn't have to be addition, maybe subtraction, maybe division. I'm sorry, maybe multiplication.
Right.
For the division, the denominator cannot be 0 either. Okay, number 56. Oh, this one is fun. Okay, find part A, the domain, and B, the inverse function. Okay, so implicitly they say, oh, this function is 1-to-1. But can you tell what's the inverse? So fx equals to natural log of 2 plus natural log of x. So we know for sure that x has to be positive, right? Because we have that here. So x has to be greater than 0. Also, 2 plus ln x also has to be greater than 0, right? This part here, composition of function. Agree? So if x has to be positive, at the same time, natural log of x has to be greater than -2, which means x has to be greater than e to the -2, which is still positive. With that said, then the domain of the function is e to the -2 up to infinity. Okay, that's for part A. Part B. The first step, if I want to find inverse function, the first step is swap, replace fx becomes y. The second step, we swap x and y. The third step, solve for y. So this one here, I change this into exponential form, e to the x equals to 2 plus natural log of y, subtract by 2, now I change this into exponential form again. So this will be e to the x minus 2 equals to 1. I know it's ugly, but simply because somebody's ugly doesn't mean that's not the right person for you. I suddenly change it to a real life question, huh? Yeah, because if ugly person is not the right person, Thomas will never get married. And simply because you look good doesn't mean you are the right person too. Okay, that's the converse actually true. Okay, the converse is true. Okay, so it's about being the right person instead of the cute person. Okay. Korean drama is only for you to watch. Don't even think to marry anybody there. That's for number 56. Oh, this is only about the inverse function. Okay, then number 64 is an interesting question. Find the inverse function. Number 64. I guess that's the last question for this part, huh? Number 64. Y equals to e to the x over 1 plus 2 e to the x. Find the inverse function. That's our step 1 already done, replacing fx by y. Second, I swap the x and the y. You can think this way though. Instead of solving for y directly, think about solving for e to the y. So our purpose will be first get e to the y by itself. That's our plan. Okay, that's our plan. Now, e to the y without y on the right-hand side. Then the next step will be y equals to natural log of whatever that dot 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 be. Okay, so instead of, if like, this is not related to, the idea is the same. Okay, people say the key to a woman's heart is her what? Life lesson, by the way. Not always true, but in general, that's true. Anybody can tell me? Food. No, that's for guys. Key to a man's heart is his mouth. So key to a woman's heart is her ear.
Okay. Yeah. God, I'm a woman. I didn't even know that. Dang, what the hell?
Of course, this is not true in general. I mean, it's not true all the time, but in general, I was told that's true. Okay, that's why I was. It's like if you one way to approach a guy, I was told, is like to feed him, give him good food. Okay, and when you want to conquer a woman's heart, tell her nice things. Okay, say things in a nice way and say nice things. Okay, now that answered the question, how can an ugly guy like Thomas marry a cute girl like Thomas' wife? Does it answer? Because she fits me. And I know how to say nice things to her. By the way, again, this is not all the time true, but I was told that this is in general true. I heard this actually from a psychologist, not only one, some psychologists, but one of them happened to be a pastor at my friend's church. Okay, this pastor did his psychology PhD in psychology at USC, and he did research in family therapy. And he says that sometimes a guy just don't know how to talk. So if you want to keep your wife, like your marriage good, guys, things that you need to learn is how to say things nicely, which is actually one of my very big weakness. You know, just listen to the way I talk to you and try to project it to my wife. Then you know my wife actually suffers so much, right? Good thing that she is someone who is like willing to cook, even though it may not be perfect, but it's actually good. So his, oh, somebody said that his belly. Yeah, that's right. Okay, fit him. Okay. So instead of attacking his heart right away or her heart right away, attack his mouth first or his ear first, her ear first. Okay, instead of attacking y directly, attack e to the y first. Okay, so step 3, multiply by the denominator. Let me shift this down. X plus 2x e to the y equals to e to the y. From here, I put e to the y together, right? So x equals to e to the y minus 2x e to the y. And then factorize e to the y. Then I get x over 1 minus 2x equals to e to the y. Therefore, then you see that I already solved for e to the y. Now I change it into log form. Okay, that will be my inverse function. So f inverse x will be natural log of x over 1 minus 2x. Remember, one of the big question is this, like in this question here, I can ask you what's the domain. But I think the domain question for this function is easy, right? The domain, I think all x is okay at the on the top, and the bottom can never be 0, right? The bottom can never be 0. So the domain will be all real numbers. The harder question is what's the range? What is the range of that function? Now, to answer the range of this function, take a look on the domain of the inverse. Okay, yes, that's right, domain of the inverse. Oh, I'm happy you remember that. It must be from Thomas' class. Now then, how do we find the domain of the inverse? Look at the inverse function. Under what situation this will be okay? So you see that x over 1 minus 2x has to be strictly positive, right? That's the domain of the inverse, right? Once you solve that, once you actually no, not all real numbers excluding 1/2. I don't think so. It has to be strictly positive. So for us to solve this, you need to go through these steps. The critical numbers on the top, x equals to 0. At the bottom, x equals to 1/2. Second, I do sign graph. 0 and 1/2. This will be 0 here. This will be undefined. This is positive, negative, positive. So the domain of the inverse function which is the range of the function is from negative infinity to 0, not including 0, union 1/2 to infinity. Okay, so you need to do, when you solve non-linear inequality, make sure you go through this process. Make sure you go through that process. Don't believe your eyes just by just looking at that. No. Okay. Feeling is not a good guide. It's a guide, but it's not always a good guide, especially at this level. Okay. Let's do some little experiment. In case you want to graph this, I happen to have a graphing software here. Okay. Let's graph that and confirm that the range is has to be negative or greater than 1/2. Y equals to e to the x. I think that's not the equation. Give me a second. Okay, yes. E to the x d5 d5. What's that? 1 plus or 1 minus? 1 minus 2 e to the x. Is it right? Is that the function? Oh, plus. It's a plus. It's a plus here. Why do I get something totally wrong? Oh, I forgot the natural log. My bad. So coming back here, I'm sorry. Coming back here. I forgot the natural log. So that has to be positive. That's right too. So if I apply natural log, to that, it will be, why am I confused? That's the domain. Because I get the opposite instead. Ah, I know my mistake. I make a wrong sign here. I know my mistake. It should be minus here, plus here, and then minus here. See, when x is 2, for example, it's negative. When you plug in x equals to 2, like I do testing point, 2 over 1 minus 2 times 2. That's negative 2 over 3. That's negative. Oh, good thing I checked that with my graphing, though. Otherwise, I missed that one. I'm sorry. So it's supposed to be the other way around. So this is actually from 0 to 1/2. Okay, that's the range of the function, which is the domain of the inverse function. Going back to our graphing, that's the graph. To emphasize the 1/2 and 0, let's add more equation. Y equals to 0, that's the lower bound. And then y equals to 1/2, that's the upper bound. So you see that the graph, which is in purple, never passed the blue line. Right? Never passed the blue line. See that? Okay, and the purple curve never passed below the x-axis. Okay, that's for this part here. Go back to my notes. It's 8:44. Let's take a little break from this 6:3. After this, we will do 6:4. But let's take a little break. We come back at 8:55. Is it okay? But prepare your question though. Prepare a question. And your focus should be in 6.4. The focus of this calc 2 is supposed to be, instead of 6.3, supposed to be on 6.4. But okay, let's take a break first and then we come back later on. Okay, let's start again. From this 6.4. So far I didn't, oh shoot, I didn't pause it. Okay, my bad. So it's still recording during the break. I'm sorry. Let me go on. This 6.4, the key. Let y equals to natural log of x. So the derivative of natural log of x is 1 over x. Okay, now from here, there are two possible outcomes. The first one is the antiderivative. So if dy dx equals to 1 over x, then what will the, remember, like if I massage this is 1 over x dx, right? Okay, so the integral of dy is equals to the integral of 1 over x dx. That's equals to y equals to integral of 1 over x dx. Of course, plus constant. But my y is ln x. Okay, so if the derivative of ln x is 1 over x, then the integral of 1 over x is ln x. Don't forget plus constant. That's one. The other thing is this. We get chain rule. So what happens if we have y equals to ln u, where u is a function of x? So y prime, the derivative of that will be 1 over u times u prime. Okay, or simply u prime over u. Other thing. So from this one result here, we come up with the antiderivative, what happened with the chain rule, and what happened if the base is not e. So log base b of x instead. Then we do change of base. This is natural log of x over natural log of b, which we can rewrite as 1 over natural log of b times natural log of x, such that the derivative is the change of base, natural log of b, times 1 over x. Now, that's the key for this section. Okay, that's the key for this section. Now, let's go on. Any question from this section? We start from a simple one, number 4.
Wait, Thomas, can you give me 1 sec? Can you scroll back up first?
Only 1 second. Okay, you ask for 1 second, you get 1 second.
Oh, my lights turned off. That's why. So I missed this part. I'm sorry.
Okay, that's okay.
Thank you.
Mm-hmm. So number 4, function fx equals to natural log of sine squared x. The derivative will be the derivative of,
Thank you, Thomas.
okay, the derivative of ln blah is 1 over blah times the derivative of blah. Let me do it this way first. Okay, so now I polish that. This is 1 over sine squared x, and the derivative of sine squared is 2 sine x cosine x. Right? The sine cancel. the sign, one of the sign cancel. So I get 2 cotangent x. Okay, notice that somebody may do it this way, which is not really appropriate, but okay, for now the result will be the same. Notice that fx is the same to 2 natural log of sine x. You see that? Because this is the exponent of the argument, right? So I can bring it to the front. Okay, now then the derivative of that will be 2 times the derivative of natural log of blah is 1 over blah times the derivative of blah. Okay, but we come up with the same answer, 2 cotangent x. However, be a bit careful. These two functions here are not exactly the same. This function and this function are not the same. Okay, why, Thomas? Why they are not the same? Notice that the guy in the argument here almost always positive. It's sine squared. It's sine squared, right? So only when sine x equals to 0, it will be undefined inside the natural log. However, sine x here has a lot of intervals where it's not defined. For example, quadrant 3, right? Quadrant 3 will not be in this in the domain of this function, while it is still, quadrant 3 is still in the domain of this function. Okay, so these two functions is not exactly equal. No, they are different in the domain. Now, the nice thing is actually, even if you do it, the one on the right-hand side, you still come up with the same answer. Okay, that's strange. I'm not saying that you can always do it that way, though. No, no. The right-hand side happens to be the same. So let me put it this way. This method is questionable. This method is questionable. Why? Because you already changed the domain. Okay, that's for number 4. How about number 6?
Yeah, Thomas?
Yes,
Could you give us an instance where that would not work? Or are you saying that it would still work, but the domain would? I'm just a little confused. And
oh, it just maybe we better say it this way. It just happened that both of these come up with the same derivative.
So it won't always work, is what you're saying.
The one on the left-hand side is always true. It's true in this case.
The second part of it, sorry.
Yeah, the second part is not always true. But put it this way. There's a question in pre-calculus. And that question seems to be an easy question, but actually it's not. The question is solve natural log of x squared equals to 2 natural log of x. Solve that, and then not only my students, a lot of students from other sections, because I usually walk to the library, right, the tutoring center, and even the tutor says, oh, the solution is all real number. But no, the way they think is like, okay, well, by this third property, you can move the exponent to the front, right, the third property. But there's a requirement for that to be true, though. The third property says that if the argument is positive, then ln x to the n equals to n of ln x. So they forget this requirement.
Okay.
Okay, now, so go back to this question. So what's the solution for this, Thomas? Well, the solution will be, solution will be all real number, but at the same time, the x has to be positive. So if you combine those two, the answer will be 0 to infinity. Not all real numbers. Not all real numbers. You can try. Let's say if I use x equals to negative e. If I use x equals to negative e, notice that on the left-hand side, it is equal to 2. Right? Because ln of negative e squared is ln e squared. Right? You see? But ln e squared equals to 2. Now,
Right.
ln negative e is undefined. So the answer is not all real numbers. The difference is the left-hand side has different domain to the right-hand side. Yeah, the domain on the left-hand side is all real number except 0.
Okay, okay.
Right?
I think I know.
Yeah, on the right-hand side it's only positive, not even 0.
Ah, okay.
So that kind of difference may distort our final answer. Okay, so number 4, what I want to say is this. Number 4, it seems like we can do it this way, but that method is actually questionable. You already changed the domain.
Got it. I
Okay? Yeah,
I
you already
understand a
changed
lot
it.
better now. Thank you.
Okay, now number 6, if the function is 1 over blah, then what is the derivative? The derivative of 1 over blah is, let's see that as 1 over u. Okay, so that's equals to u to the negative 1, right? Okay, so the derivative will be negative u to the negative 2 times the derivative of u. Is it right? Now change that u back. Let me write it this way, then this is natural log of x to the power of negative 1. Maybe I write it that way better. So the derivative of natural log of x to the power of negative 1 is negative of natural log of x to the power of negative 2 times the derivative of natural log of x. This is negative 1 over natural log of x being squared times 1 over x. So that's negative 1 over x times natural log of x being squared. That's for number 6. How about number 8? Number 8, fx equals to natural log base 5 of x e to the x. Now, because the base is not base e, then the derivative, you need to do the change of base first. 1 over natural log, 1 over natural log of 5 to change the base to natural log. Well, because this is natural log of x e to the x over natural log of 5. Okay, so that's 1 over ln 5 times the derivative of this. Okay, the derivative of that. Now, the derivative of that is 1 over x e to the x times the chain e x times e to the x. So this is the change of base. Okay, and the derivative of natural log blah is 1 over blah times the derivative of blah. I do the change of base first. Now then put things together. This is 1 over x e to the x natural log of 5 times. Now then this part here, you need to do product rule, right? You need to do product rule there. That will be 1 times e to the x plus x times e to the x. That is e to the x. You know what? Let me factor e to the x on the top. E to the x plus times 1 plus x over over x e to the x natural log of 5. If I cancel e to the x, I get 1 plus x over x natural log of 5. Okay, now notice that this can also be seen as 1 over natural log of 5 times ln x plus ln e to the x, right? I split this. I split this here becomes sum of logs. Log of product equals to sum of logs. But that expression is the same to 1 over natural log of 5 times ln x plus x. So what is the derivative? That's 1 over ln 5 times 1 over x plus 1. See, it becomes 1 plus x over x ln 5. Turns out to be the same again. Okay, now this phenomena is actually considered, for now we cannot answer this question yet. Why that, even though, you see what happened here is this though. The domain here, oh, the domain actually the same. The domain is actually the same. This can be on positive only when x is positive. So the domain are the same actually. They are exactly the same. They are exactly the same. So the derivative will be the same also. So you see that I do 2 different ways to do the derivative there. So yes, this will be the same, no question. That's number 8. Is there any question you would like me to do between number 9 to number 25? Otherwise I get bored. Maybe 2 more questions from here. To make the case even stronger, it turns out that this is still true even if you have absolute value here. That's still true. Okay, that's still true. So that is still true here. And we anticipate what will happen later on when we do integration. Number 12, maybe. That thing looks strange. Hx equals to natural log of x plus square root of x squared minus 1. I have a chat message coming in. Number 16. Okay, I will do it after this one. So the derivative of this function is 1 over blah. It's already natural log, right? 1 over blah times the derivative of blah. Okay, which is 1, you know what, 1 over x plus square root of x squared minus 1 times 1 plus, oh, what is the derivative of that thing? X over square root of x squared minus 1, right? I don't think I will do the multiply that in right away. Let me fix the guy inside the parentheses first. I think it turns out to be a very nice thing. So the guy inside the parentheses, if I simplify that, it becomes square root of x squared minus 1 plus x over square root of x squared minus 1. Simplifies to be 1 over square root of x squared minus 1. Am I doing any mistake here? I don't think so. So this actually tells us something. This actually tells us something. So later on, integral of 1 over square root of x squared minus 1 dx, this is equals to natural log of x plus square root of x squared minus 1 plus constant. Okay, that's what we get. But we will prove that another way once we get to chapter 7. We'll prove that another way once we get to chapter 7. For now, we see, oh, you know what? If I simplify further, then the answer gets quite simple. How about number 16, Thomas? I think your issue is with the absolute value. But actually, that's not to worry, because we know if y equals to natural log of absolute x, the derivative is still 1 over x. So what is the difference between y equals to ln x and y equals to ln absolute x, Thomas? The derivative the same. Can anybody tell me the difference between these two functions? The yellow one and the blue one. What's the difference?
The absolute value would allow you to have a negative value for x.
That's right. So basically the difference is with the domain, right? The domain of the blue one, only positive x, right? For the yellow one, positive or negative x are okay except 0. Okay, the derivative, however, of course, if you use the yellow one, okay, the derivative of this applies for x positive or when x negative, right? But if you use the blue function, then the derivative only applies for the positive x, because the function is not defined. The function is not even defined when x is negative. You see that? Okay, the restriction is with the domain. The restriction is with the domain, even though the derivative seems to be the same, right? But the domain is different. Okay, now then, using that idea, what happened if we have, so when y equals to ln of absolute 1 plus t minus t cubed, the derivative will be same thing, 1 over 1 plus t minus t cubed times the derivative of this thing. Oh, sorry, I missed the prime, which will give us 1 minus 3t squared over 1 plus t minus t cubed. Okay, I hope that answers the question about what happens if we have absolute value. Nothing really, nothing really. Okay, that's for number 16. Other question, maybe one more question. From this part. Number 22 maybe, that looks ugly. Number 22, y equals to natural log of absolute of cosine of natural log of x. Wow, that's a lot of chain rule here. So y prime equals to 1 over cosine of natural log of x times the derivative of cosine of natural log of x. The derivative of cosine is negative sine of natural log of x times the derivative of natural log of x. Let me use this notation, even though I know derivative of natural log of x is 1 over x. So this will be negative tangent natural log of x times 1 over x. Let me put the negative right in the middle. That's for number 22. Logarithmic differentiation. So from number 44 to number, what's that, to number 43 to number 54. Logarithmic differentiation, especially being used if you have, especially used if we have a function of x taken to the function of x, especially. Okay, logarithmic differentiation is especially used if you have a function of x to the function of x. Just for example, suppose I have let fx equals to x to the x. What is the derivative? Okay, I think this is a very standard example everywhere. The way we do it, find the derivative of x. The way we do it is you apply log first. Log, natural log, I mean, natural log of fx equals to natural log of x to the x, which give us x natural log of x. Now, then you apply implicit differentiation. Apply implicit differentiation. When you do implicit differentiation, you will get 1 over fx times f prime x equals to, on the right hand side, you do product rule. 1 times natural log of x plus x times derivative of ln x is 1 over x. So f prime x equals to fx. I multiply both sides by fx. So the right hand side becomes fx times natural log of x plus 1. In other words, the derivative of x therefore is x to the x times natural log of x plus 1. This is a standard example in class. Another example that is very, very close to that, for example, number 48. Y equals to x to the cosine x. Find y prime. Solution. Apply natural log first. Now that natural log will change the exponential function into product of log. That's cosine x times ln x. Now then from here, you do implicit differentiation. Notice that it is now doable on the right hand side. It's negative sine x times ln x plus cosine x over x. So y prime is now equals to y times cosine x over x minus sine x ln x. I'll change that y back. That's x to the cosine x times cosine x over x minus sine x ln x. Phew, that's messy, huh? I remember there was one time I asked a triple X question. And I did say adult only. No pun intended. Let y equals to x to the x to the x. Find y prime. So to do this problem, let me give you a brief sketch of what should be done. So you apply natural law, correct? So you'll get x to the x of ln x, right? Okay, now then when you do implicit differentiation, you will see that you need to do x to the x prime times ln x plus x to the x times 1 over x. Now the thing is, how do you do the derivative of x to the x? Then you do it aside. You kind of interrupt your work, and then you say let fx be x to the x, and then you do the derivative. Which, as I remember, we already had that earlier, x to the x times ln x plus 1. Now then you go back to the main story. So 1 over y times y prime equals to x to the x times ln x plus 1 times ln x plus x to the x times 1 over x. So y prime equals to x to the x to the x times x to the x ln x times ln x plus 1 plus x to the x minus 1. I don't ever want to see an x again. That's why you call that your x. That's why you call that your x. Like, he is my x. She is my x. I don't want to see x anymore. We are talking about different x. We're talking about different x. Okay, number 55, I think is a, oh, you know what, number 56 right away, why not? Number 56. We are not even doing integral yet, and I only have around 20 minutes left. So number 56, let x to the y equals to y to the x. Ooh. Okay, so find y prime. Apply natural log. Ln of x to the y will be equals to natural log of y to the x. Therefore, we get y ln x equals to x ln y. Now then, you do implicit differentiation. You'll get y prime ln x plus y times the derivative of ln x is 1 over x. On the right hand side, implicit differentiation give me ln y plus x times 1 over y times y prime. Now let me rearrange now. So y prime ln x minus x over y prime equals to ln y minus y over x. You know what? I don't really like this. Let's multiply by the LCD xy just to clear up the denominator. So if I multiply by xy, then
Real quick, Thomas.
Uh-huh.
Or wait, I got it. Never mind. You're good. Sorry.
So I will get xy ln x times y prime minus x squared y prime equals to xy ln y minus y squared. So if I factor the y prime here, xy ln x minus x squared equals to this. So y prime is equal to xy ln x minus y squared over xy, oh I'm sorry, it should be y here. Should be y here. xy ln x minus x squared. Man, that's quite nasty, huh? Hey, trust me, it's not something we can say, oh, you know what, Thomas, I'm so smart. I look at that question, I know the answer. Nah. Okay. You need to show the word. That's for number 56. Let's do integral. So for the integral, then we know integral of 1 over x dx is ln absolute of x plus constant. Okay. So let's say we do number 74. Number 74, integral from 4 to 9 of square root of x plus 1 over square root of x being squared dx. I will FOIL this first. I think foiling that will be a lot easier. So if I FOIL that, the first term being squared is x. The second term will be 2 times a times b plus b squared. Right? So this is integral from 4 to 9 of x plus 2 plus 1 over x dx. This will be 1/2 x squared plus 2x plus natural log of absolute of x from 4 to 9. But we subtract from the top though. We subtract from the top. It will be 1/2 9 squared plus 2 times 9 plus ln 9 minus 1/2 times 4 squared plus 2 times 4 plus ln 4. Okay. I think you can just compute it yourself. Or do you want me to compute it for you? It's 40.5 plus 18 plus ln 9 minus 8 minus 8 minus ln 4. 16.2. So this is 42.5 plus ln 9 over 4. Number 76. Integral of sine of ln x over x dx. Remember the principle of ugly guy? If something is not on its place, ugly, do substitution. Okay, so let u equals to ln x. So du will be 1 over x dx. But 1 over x dx is basically this expression here, right? That's our du. So this becomes integral sine u du. Is that right? That's negative cosine u plus constant right away. But we are not done. We need to substitute the u back. Okay, let's see. Negative cosine of ln x plus constant. That's number 76. I think number 82 is good. Should we try number 82? Number 82, the uglier, the better. Okay, integral of x 2 to the x squared dx. I think I do substitution first. So u equals to x squared, such that du is 2x dx. Now I have x dx already. Okay, so du over 2 equals to that x dx, right? Then the integration becomes integral 2 to the u du over 2. Right? See the substitution? Okay, so we now get...
Question, Thomas. What? Could you also just move the 1/2 over to the left side of the integral too?
That's what I'm gonna do. Yeah, that's what I'm gonna do. 2 to the u du. But here we have some issue. What is the integral of b to the x? We know integral of e to the x is e to the x plus constant, right? But what happens if we change the base? What will that be? So that's actually a question we're supposed to answer first. Let's do that first. Let's do that first. Okay, let's do that first. We start from the following. So I'm about to derive a formula that you should remember. Okay, note. If y equals to b to the x, what will the derivative be? There are two ways to do this. Okay, there are two ways to do this. I show you the one I like first, the first way. You do logarithmic differentiation. Okay, so ln y equals to ln b to the x. In other words, ln y equals to x ln b. So you see this ln b basically the coefficient of x, right? Such that the derivative, if you apply the implicit differentiation, the right-hand side basically ln b. Okay, so y prime equals to y times ln b. To put it into perspective, I put the y back. That's b to the x ln b. Okay, as if we are saying a little example here. If I have y equals to 3 to the x, then y prime will be itself times the change of base. Okay, or if you want to make it uglier, let's say y equals to 5 to the cosine x. Then what is the y prime? The y prime will be itself times the change of base times the chain from the exponent. Okay, so the derivative will be negative sine x times ln 5 times 5 to the cosine x. Now that's the first method. That's the first method. Another method. Another method. Instead of applying natural log, okay, I change this into log form. So log base b of y equals to x. Now apply implicit differentiation again. So we don't run away from implicit differentiation. Okay, implicit differentiation. If we have natural log of y, the derivative is 1 over y prime. But what if we have different base? Then I do 1 over log natural log of b first, the change of base part, times 1 over y times y prime equals to derivative of x is 1. Okay, so what I did here is implicit differentiation. What I did here is implicit differentiation. Then y prime equals to y times natural log of b. But the y is b to the x. Now that tells us this though. Okay, so if derivative of b to the x respect to x is itself times natural log of b, what happened to the integral? Okay, the differential of b to the x equals to b to the x ln b dx. I apply the integral. Apply the integral. On the left-hand side, I get that b to the x plus constant equals to, on the right-hand side, natural log of b is just a coefficient. So integral of b to the x dx is itself divided by the change of base plus constant. Okay, so going back to that, going back to here, oh, I need to pinpoint which one I did first. From here, going there. Going here. So what is the integral of 2 to the u with respect to u? That will be 1 over ln 2 for the change of base times itself plus constant. Okay, which if we simplify will give us 2 to the u minus 1 over ln2 plus constant. Or you can also say 2 to the u over 2 ln2 plus constant. That's also good. Okay, either one is okay. Okay, let's apply this one more to the previous question number 81. And then after this, I want to show you something very interesting.
Sorry, Thomas, could you scroll back up? I'll take a picture.
Yes. I will save this later on and put it on PDF on the discussion board. In case you miss it, let me show you what I meant. If you go back to our discussion board, like the one we have last time, right? I will put the note here. The discussion we have last time, I will put the notes here.
Okay, awesome.
Okay, yeah, but I mean, if just like this, I rather you tell me, oh, Thomas, can you scroll up a little bit? And I will just do it for you.
Also, Thomas, I think I've forgotten to sign in or do the discussion board to put that I'm here. Could you make it so it notifies us?
Can I make it what?
So it notifies us. You know how like when we're on our dashboard, it kind of gives us like things to do.
Oh, the thing is, like, if I put it as a discussion, there's no way for me to do the notification thing.
Oh, okay, I understand.
You know?
Got you.
Yeah. It's not I mean, if I see it, that I will have done it, but I mean, I thought about that also before, but there's no way for me to do that, unfortunately.
No worries.
But don't worry about it. Yeah, don't worry about it. Just sign in for the one today, and you're fine.
Sure. Yeah.
Okay. Yeah. Now, let's say this number 81 here. Number 81, integral of between 1 to 2 of 10 to the t dt. Do we need to sign in even if we show up on Zoom? Yes. Yes. Sign in even if you show up on Zoom. Because I don't really see you actually here. Unless you actually start to speak up, right? Then I will see that you are here. But even that, I don't remember when you are here. I mean, I know you are here, but I don't remember, like 10 days from now, I don't remember which day you were here. So for formality, you put it there. The attendance is not for me. It's more into in case if the college suddenly want me to show them the attendance sheet. So then I will show them, hey, you know what? My students attend the class and this is the evidence. Okay, now the integral of b to the x is 1 over natural log of b times b to the x from 1 to 2. Okay, and then this is 1 over ln 10 squared minus 10 to the 1, that's 90. So 90 over ln 10. Okay, that's for number 81. Now, I would like to do something that you have not seen before, but it will speed up your computation by big time. Do you know that we have a quiz due next week, next Saturday? Do you see that? You always need, you always need to check that assignment part.
Yeah, it's under the assignments tab, right?
Yeah, it's an assignment. You have quiz 1, 2, right? And it's due. Don't wait until next week to do it though, because this weekend I may just suddenly give you another quiz that is due on the 28th, like let's say. Okay, and then on Monday suddenly I think, oh, you know what? I want to give you another quiz. And then if you postpone everything to Saturday, you then realize you have 10 quizzes due. I don't think I'm that crazy, but realize that I'm crazy enough. And that's what put me here. Okay, I have this one type of question which I hope can speed up your computation a little bit. The integral of mx plus b dx. Of course, this integral, you can do it regular way. This is 1/2 mx squared plus bx plus constant, right? Okay, but I want to show you another way to do this. Suppose I'm crazy enough to do substitution. Let u equals to mx plus b. So my du will be m dx. Yes, I'm crazy enough. So then when I do substitution, then mx plus b becomes u, my dx becomes du over m. Right, so I have 1 over m times 1/2 u squared plus constant. This is 1 over 2m. I substitute the u becomes mx plus b squared plus constant. But Thomas, they look very different. Hold on, slow down. Okay, this is 1 over 2m. Let me FOIL this. M squared x squared plus 2bmx plus b squared plus constant. If I distribute 1 over m, I will get 1 over 2mx squared plus bx plus b squared over 2m plus c. Notice that they are very similar to the one up here. The difference is that I have this extra. But notice that this is basically another constant. I call it C1 and call this C2. C1 plus C2 will give us another constant. C. Now they are the same. Okay, but my point is the following. If integral of integral of x dx equals to 1/2 x squared plus constant, then what will integral of mx plus b dx? I want you to realize you basically substitute that x by this guy. Okay, you basically do that substitution with 1 over m in front of that. Okay, so if you substitute your x by that with extra coefficient. Why do I say that? Why do we need to know that, Thomas? Here's the thing. Suppose, well, you know that integral of cosine x dx is sine x plus constant, right? You know that. So what kind of difference if I change that x inside the cosine by, let's say, 3x plus 5 dx? Now you will see this is actually equals to sine of the same argument. Okay, but then the coefficient 3, the coefficient of that x becomes 1 over 3 here. Okay. If e to the x, integral of e to the x dx is e to the x plus constant, what will happen to integral of e to the 4x dx? You will see that's 1/4 e to the 4x plus constant. that's what happened. Okay, that's what happened. I guess that's where I want to stop. So on Monday, when we come back, we will do 6.6 and 6.7. Let me see it again. No. I'm sorry. I don't do hyperbolic. So I will do only 6.6 and 6.8. On Monday, we will do 6.6 and 6.8. And therefore, we finish this chapter 6 on Monday. Okay, then. See you on Monday.
Thank you. Have a good